this sound. Sound characterized by both frequency and intensity. And we will try to use both these two characteristics of sound to find different methods to derive the result. So at first we try with Doppler effect, and then we will use the intensity using air absorption and typical spheric wave behavior of sound. So let's proceed. At the beginning, we'll try using frequency. So if we use frequency, we'll use for sure Doppler effect. Here you can see the formula of Doppler effect. This is the speed of the observer, like here, for example, the clock, and here we have the speed of the car. Actually, if we let's give some numbers to have an idea of the shift that can occur. If the car is moving at 8.3 meters per second, and we think about the typical frequency of an engine of 1.5 kilohertz, we would have a shift of about 40 terahertz. This is quite a tiny shift if we think that the human ear resolution is just about 2 hertz. But actually, this resolution for human is just for the idea is that if you can distinguish two different frequencies if you can hear them purely. But actually, we don't hear them purely because we have a white noise above our spectra that makes them less understandable. And also, we cannot hear single frequencies because we have different car signature, like many different frequencies that are kind of very difficult to the difficult signature of the car. To measure this shift, we could actually perform an autocorrelation of the spectrum, but even those could be very difficult to do because different frequency actually has different shifts because of the formula I showed before. So let's go on. So if we actually try to use a Doppler effect of the axis, so this formula is the formula for the frequency, and as you can see here, we have we can use this formula using the car motion, and we can arrive to this formula and try to see the data. Actually, we didn't do that because of these things. If you think before 30 meters, when the car is at 30 meters, the cosine is about 0.986. And at the infinity, when the car is very far away, it is 1. So if you think about typical distances, for example, this distance, we put it at 5, we would have a shift of 0.4 hertz. That is so tiny, and we could never distinguish it from noise. So we thought that it would be really better to use intensity, actually. What is intensity? Intensity is both characterized by a spheric wave and air absorption, as you can see here. And if we could actually write this system equation in which here we have the initial distance, here we have the integration speed, and so we could have an expression for the intensity in function of time. So the detector, we use to detect our data. We use a normal smartphone using this application to have data, and we remember the data were obviously taken in dB, and this is the definition of dB. In trying actually, this is the solution of the formula the system I previously written. We have R depends linearly with T. So here the intensity depends linearly with the time here, and logarithmically with time here. The fit does never converge, even if we initialize these 3 parameters. Why? Because this fit is actually very difficult to do, and also because of this. Here we plotted the recorded intensity in dB in function of time, and we can see that if we try to fit here at a distance bigger than this, the curve is quite linear, it's pretty linear, and with a small tuning of the 3 parameters I've written before, we can fit the same curve with really different parameters. So that is really reasonable that the fits cannot actually converge, or at least converge with huge errors. So, since we have linear behavior, we try to make some approximation, for instance, using the fact that if the behavior is linear, you can actually use only the exponential behavior, if you think about to be at a major distance. If you compute our result, we expect to have here now a linear behavior in time if you just use this exponential. So let's go on. Now here we have the need of characterize this value, this beta that represents a sort of air absorption. So to do that, we use the car engine. The car was actually stopped, and we measured the sound at some different steps here. And then we know that beta depends a lot on parameters, that climate parameters we are in, so humidity, atmospheric pressure. Beta also depends on the frequency of the car, so we need to use that as a given frequency and temperature for sure. So we actually here estimated beta at different frequency. We fixed, these are the data. We use an interpolation function, and we find a value of beta of 0.043 meters to the minus 1. And here we have the 95% error. Now, here we have the intensity analysis. Here we can see the data in time, and this is before 30 meters. As you can see here, we have the lead is hidden in the coefficient of this regression line, and so if you know the coefficient, we can actually find V. So with those, we did several measurements of obtaining. We set an electronic in the electronic of the car. We set the speed. So 30 meters and 40 meters. We took several measures, and we had a mean result of 35 kilometers per hour here and 48 kilometers per hour here. But the interesting thing is that here we have huge errors. As you can see, it's more than 10 for the lower limit and 6 for the upper one. The thing is, debate that an estimation of beta is the very limit of precision, since the estimation of beta is the very limit of precision, since it's very hard to have a very precise estimation of beta because it depends on a lot of parameters. But we also need to take into account other sound sources. For example, the white noise that is on the street. If you are in an industrial area, maybe we have some noise, and so this could really ruin us measure because we are measuring intensity of sound. We cannot concentrate on just one source. And we could have also different sound sources in the street, in a busy street, that could destroy our measure actually. For example, if another car passes by, we cannot actually say that we cannot not to take into account that car. We can have wind, and wind can make a white sound above, and this could actually destroy our car. And also a small movement in the setup can actually, a small movement in the microphone could change our results. And at the end, also the buildings, it's a second source of error, but actually we lose we can have the sound can be kind of concentrated in the street. So we lose the typical reflectant and so on absorbed by the buildings. So this is a source of error that is very difficult to take into account. And last, let's drop to the conclusion. We demonstrated that the Doppler offset cannot actually be used in a very effective way, and we demonstrated that the exponential fit can actually be used. As you can see, we managed to have some results with that, but we can safely say that the rumor is not confirmed that a cop cannot actually really understand the speed of a car just listening to sound, because the error on the estimation is way too big. So, thank you for your attention.